take it out.
Yes, yeah, thank you for the introduction, and yeah, it's great to see this thing kicking at the beginning of this operation. Yeah, so indeed, I wasn't planning on cover everything about AI or machine learning in physics because it's a bit too broad to do in 30 minutes. So I wanted to just maybe focus on what we do in my lab, so that we can also try to find maybe common collaborations, common themes. So I will give you an overview essentially of that. But okay, I will first give maybe a short introduction on some ideas of machine learning that might be useful for the discussion, and then I will tell you about what we call neural quantum states and how they fit within the three main paradigms of machine learning, so supervised reinforcement and unsupervised learning. So essentially, yeah, so machine learning, as you know, I mean, is the answer to an ancient desire of humanity, right? So to have machines that are able to think, right? So to have some automaton that does that, and we've seen many applications of this intelligent software, so to speak, that can be used for many tasks, from automating some tedious tasks to discovering potentially new drugs, or translating language and other things like helping us with physics, which is a more recent, if you want, development in the field. So there's maybe somebody who's not gonna. Right. Okay, so then, I mean, there are two ingredients in machine learning. So the first one is definitely the machine, and the other one is the learning. So the machine, especially in modern machine learning or in modern deep learning, if you want, is essentially an artificial neural network. And an artificial neural network can be seen as a idealized version of what a brain, an actual brain is, right? So in this sense, I mean, we mathematically model a brain as physicists, or not even physicists, but as mathematicians, if you want, as something that takes some inputs, for example, I don't know, the things that you see from your eyes, and then elaborates some outputs, for example, some thoughts or some output of your brain thinking. And you can see this as a clearly high nonlinear circuit of synapses that is activated by these inputs. So, and in this sense, I mean, you can model this as a function, if you want, a very complex function, f of inputs x, and with potentially many outputs that I go here, for example, with only two outputs, f1 and f2. And then there's all sorts of weights or sort of parameters that somehow describe how this signal is transformed. And again, this is a very simplified description of how a brain works, in the sense that if you look at the actual physiology of the brain, it's much more complicated than a simple function. But I mean, it's like assuming that the cow is spherical, I mean, to first approximation. So we have a function. And then again, within this spherical cow approximation, we have an approximation of the brain is given by these artificial neural networks, which are the mostly widely used deep networks that you can see used in many applications these days. So where essentially, again, you have an input that could be a vector of values. And then this vector of values is transformed by some linear map, some affine transformations, so for example, by some matrix W that is applied on these inputs X. And then component-wise, you apply a nonlinear transformation G to this vector. And then you repeat this operation many times until you reach the final layer that you can see here. Here we have only one intermediate layer and then one output. But this operation in principle can take place many times. So this really mimics how the neurons work in the brain, in the sense that they receive some electric signals and then they start activating or not, depending on the incoming electric signal. So this thing is typically mimicked by the presence of an activation function G that is nonlinear and that starts spiking, for example, when the input is larger than a certain value. So mathematically, I mean, besides if you want, the physiology of the brain, I mean, there are some guarantees that you can represent arbitrary high-dimensional function using this composition of linear and nonlinear transformations. So specifically, there's a theorem by Kolmogorov and Arnold that guarantees that with only two layers of this architecture, actually, provided these nonlinear functions phi and capital Phi and small phi are good enough. You can describe any essentially continuous high-dimensional function f of x. And notice that this summation goes up to n, where n is the dimension, so the input dimension of this x. So it's not an exponential summation, as you would typically have instead if you do a linear expansion in a basis, let's say in Fourier basis. So the fact of working with a nonlinear function allows you to have, in theory, a linear summation in these things. Of course, all the complexity now is hidden in this nonlinear function, phi, capital Phi and small phi, but at least in principle, it's possible to find this kind of representations. Then, I mean, once you have a machine, you have the learning. So again, maybe most of you are familiar with this, but the most common task that you can do with machine learning is supervised learning, so the simplest conceptual task that you can do. So this is essential data fitting in the sense that you have a data set where you have some pairs of x and y. So essentially, you have data points where you know that the value associated with this x will be some value y. And you want to fit this function, for example, in neural network by minimizing some loss, as you call it in jargon. So essentially some discrepancy between the prediction of your function computed on these data points x and the output that you expect. So for example, this L could be just the L2 difference, so the square of the difference between the output of f on the given data points and y, so what you expect. So a typical task, the simplest task that you can think of is, for example, like recognizing numbers. So in this case, you have an image, so x would be the pixels in these images. And then some of these pictures are pre-annotated by people, for example, and where they write that, for example, this is a 5, this is a 0, this is a 4. So in this case, you know exactly that you have a pair of x and y's, and then you want your machine to learn this correspondence, and then you train on these many images, and then you can apply your function on some unseen image, and this will output the result of this, if you want, OCR, of this optical character recognition, that is done, again, just by data fitting of existing image. Now, there are many other learning paradigms. So the other two that I will talk about today, I guess, so one is unsupervised learning, so where you have data points, but you don't have labels. So in this sense, you have some unknown probability distribution P of x that you want to reconstruct. So in this case, again, you have some data points that are given to you, and you want to find out what is the explicit form of the probability distribution that somehow is responsible for producing this data. Okay, so this is a very well-defined task, and I will give you maybe later on some examples. And then there is reinforcement learning, where you don't have data, but you have some task that you want to solve. And you have some feedback from a so-called score function that tells you how well you are doing your task. So in this sense, you don't have, again, data like in supervised or unsupervised learning, but you have a task that you want to solve, and then you adapt the weights in order to solve this task in the best possible way. So one of the early examples of this is was this was one of the first publications by DeepMind, so where they were trying to play Go, to play. So this game, actually, I don't remember the name of this game, but okay, it was a very popular brick wall or something like that, right? On Atari, when I used to play it when I was a kid. But essentially, yeah, this was one of the first applications of reinforcement learning, where the task was to maximize the score of this game. And of course, I mean, they managed to improve this, to be able to play this game quite well with this reinforcement learning approach. And by now, you see that they have become masters in many other applications that are much more complicated than this. So, so these are the three main paradigms that, again, are general, not necessarily related to physics. So what I want to tell you is maybe how some of these ideas can be applied or extended or used for quantum physics. So in this context, again, I'm interested in many body physics. So I have in mind that I have some relativistic, typically interacting Hamiltonian with some n degrees of freedom, for example, electrons or spins, and the interactions are given by let's say more or less first principles. And again, the main goal that I have here is to solve the Schrödinger's equation. For example, to find the ground state of this Hamiltonian, this interacting many-body Hamiltonian, or to solve the time-dependent version of the Schrödinger equation. As you know, I mean, this is kind of complicated if you want to do it in general on a computer, on a classical computer, because the minimal requirement that you need to have is to have a complete set of many-body states, and you need to store all the possible wave function amplitudes for all the possible potential, all the possible many-body basis states. So for a discrete system, let's say a spin of systems, a spin system 1/2, for example, you would have a 2 to the power of n possible basis states, all the possible combinations of up and down spins. And again, typically you are limited by memory because, again, if you want to simulate or store the wave function of 160 spins, this would take essentially all the atoms on our planet. I mean, just to give you an idea in terms of RAM that you will need for this task. So it's clear that we cannot do this exactly for more than 20 or 30 spins. 30 spins is around the thing that we can do these days. So there are alternatives. So in general, we don't need to store the full wave function in many approaches. So for example, one is quantum Monte Carlo, so where you sample from the imaginary time projection of some given initial state through some path integral approach, right? So this is nice because it allows you to sample the wave function rather than storing it. So you can really use this for large systems. However, it has a limitation because whenever you have a Hamiltonian with same problem, so for example, for electrons, you cannot perform this on large systems. So again, this method is limited. And then there are other families of approaches, for example, based on met-explorer states, so tensor networks. So these are very efficient in one dimension. They provide you a compact representation of the many-body state. But I mean, in higher dimension, they are less convenient to work with, and they are less, let's say, accurate than their one-dimensional counterparts. For example, met-explorer states that are instead intrinsically defined in 1D. So this is just to give you a motivation. So why we need to maybe to introduce other approaches. So again, because typically quantum Monte Carlo breaks for fermions or even for frustrated spin models. And also it doesn't give you access to real-time dynamics. So if you want to solve the time-dependent Schrödinger's equation. And met-explorer states, again, as I was mentioning, are extremely efficient in 1D, but in higher dimensions, they are less efficient. So in this context, then we can wonder how to use quantum neural networks. So the basic idea is that you represent the wave function in terms of this artificial neural network, right? So I told you that these are very good at representing potentially high-dimensional functions. So in this case, you have a brain, so to speak, that takes as inputs your quantum numbers, for example, the spin projections, and then outputs a scalar, a complex valued scalar, which is the amplitude of the wave function for this given set of configurations, if you want. And then the main complication here is to find the best network that describes or that solves a given problem. For example, a ground state problem or a dynamical problem or any other application you might be interested in. So just to give as an idea, so the early networks that we used in this business were based on restricted Boltzmann machines that you might have heard about last year because of the Nobel Prize in physics. And these are indeed very simple, the simplest, so to speak, artificial neural networks that you can think of. They only have one intermediate layer, and essentially you can control the accuracy of these networks by increasing these hidden neurons, so these hidden variables that appear in these networks. And these are used to intuitively, if you want, you can see as spins. So you can think that these objects are given as input, and these are spins, so plus or minus one in this case. And also this hidden layer is, you can see this H1 up to HM as spin 1/2, so with plus or minus values, classical pits in this case. And the role of this object is essentially to mediate the correlations between the visible variables. So you can mediate arbitrary correlations between these physical spins by using these hidden or ghost variables, if you want, that appear in this representation. So mathematically, it's quite simple. So essentially, you have a Boltzmann form. So that's why this is called a Boltzmann machine, where at the exponential, you have a sort of Boltzmann factor with an energy that contains interactions between your visible variable sigma and your hidden variables h, that again are spins in both cases. So these W's, these interaction metrics, are just parameters that you can tune and that you can learn. Okay, so these are the free parameters in this variational representation. And also you have some fields, so some external fields B and A, that are coupled to both the hidden degrees of freedom and the visible degrees of freedom. And what you do is that then you trace out, so you sum over all the possible hidden degrees of freedom. And this summation can be done analytically in this case because you don't have interactions among the hidden variables. You only have interactions between the hidden and the visible variables. So that's why you can sum these exactly. And then as in the other cases, there are some representability theorems that guarantee that you can represent an arbitrary high-dimensional function if you add enough of these hidden variables h. So to find the ground state, we are in a situation similar, but not exactly the same as that of reinforcement learning, where indeed we don't have some data of the exact wave function that we are looking for, but we have a Hamiltonian, right? So this is the only information that we have. But we don't have the exact wave function, otherwise we would have solved the problem already before using machine learning, right? So in a sense, we need to somehow determine the parameters using some principle. And the principle, of course, that we're going to use is given by the variational principle of quantum mechanics. So in other words, what we are going to do is that we want to just minimize the energy, the expected value of the Hamiltonian, over this class of variational states, and this is done. Then in this way, we will find the optimal parameters that enter this neural network. Okay, I will skip most of the details that are interesting, but maybe in the interest of time, I mean, we can discuss them maybe later on. But indeed, if you want, one interesting aspect is that to find and to evaluate this energy, one typically samples from the square of the wave function and averages some effective energy on this distribution, and then one can minimize it also using gradient descent. So again, I'm skipping all these details, but again, the idea is that you sample from this distribution of the spins, psi square, from your model, and then you update the parameters, and then you resample from this distribution. To give you an idea, some example application. So this is a recent paper that was published by a group in Germany, and they studied this frustrated spin model. So where you have a square lattice, and you have spin-spin interactions on the edges of this lattice, both on nearest neighbors and on next to nearest neighbors. So this is one model that cannot be solved exactly with quantum Monte Carlo because you have the same problem. And in this case, you can show that, okay, if J2 is 0, you can still solve it exactly with quantum Monte Carlo, and you have the exact energy. So you can compare relatively to the error, to the exact energy. And you can see that by increasing the number of parameters, so here they are not using our very old RBMs, but they are using actual CNNs, so they are using convolutional neural networks that are deeper neural networks. And you can see that by increasing the number of parameters, you can get to errors of 10 to the minus 7 or so on the energy of the ground state. And then in cases where you don't know the exact ground state energy, you can just compare to other variational states. And you can see that by increasing the number of parameters, you can reach some of the, essentially the best architecture that was done, that was available at the moment, at that time, which was an RBM, but with a complicated projection step that is removed in this paper. So in essence, what they do is that they just use a pure convolutional network, and then you can get very nicely to the lowest known ground state energy for this problem. Maybe I just want to mention another application before wrapping up, which is the application to solving for the time-dependent Schrödinger's equation, so for the dynamics of something that you cannot do, for example, with quantum Monte Carlo. So the idea is based on a time-dependent variational principle that is more general, can be used for many other variational states. So essentially, you have some variational state that depends on some parameters that here I call alpha. And then what you can do is that at each step of time, you can try to minimize the distance between the time-evolved state that is induced by a variation in your variational parameters. So now your variational parameters will have some dynamics. So that's why you have some alpha dot here. And then the exact evolution that is given by the Schrödinger's equation. So by optimizing, if you want, this distance, you can then, by minimizing this distance, you can find an optimal equation of motion for your parameters in, for example, in your neural network. Again, I'm skipping many details, but at the end, you need to solve this kind of equations at each time step, where you have the optimal time derivatives of your parameters and some quantities that you can measure or you can estimate with Monte Carlo sampling. We've applied this, for example, to the dynamics of 1D and also many other applications recently to two-dimensional problems. And you can study, for example, what happens when you do a quench. So, for example, you prepare your system in the ground state, and then you change some coupling constant in your model, and you see what happens to some local dynamics. For example, this is the transverse field Ising model, where you quench the transverse field from some value to, let's say, 1/2 to 1, the critical value in this case. And you can see how it thermalizes after some time. This is just one of the many applications that have been done in the field. Maybe actually, sorry, the last thing that I wanted to tell you is instead one application where we actually have data. So we don't have, we are not in the situation where we only, so to speak, have the Hamiltonian, but we are in a situation where we also have some data, right? So this is relevant for experiments typically, when you want to learn a quantum state from experiments. So again, this is a different situation because we are not simulating the ground state from first principles, but somehow we are given access to an experiment and we want to somehow model the ground state of this quantum system in the lab with some wave function. And indeed, the idea is that that is known as tomography in jargon, I mean, in quantum computing terminology, is that you want to reconstruct the quantum state from simple measurements of your quantum system. So the standard approach would require exponentially many measurements because you need to do a full reconstruction of the amplitudes of your system. But this is naturally rephrased in the context of unsupervised learning, because if you think about the measurement process in quantum mechanics, you know that your degrees of freedom will be distributed according to some Born distributions of psi squared. And then this is exactly the goal of unsupervised learning, as I was describing at the beginning. So you have some unknown distribution, which is your psi squared, and you want to reconstruct this with some model, all right? And then you might ask then, how do I learn the phase of the wave function? Because this is psi squared, right? It's not psi. And then the idea is that you don't measure psi in a single basis, but you measure in many bases, right? So for example, not only in real space, but also in momentum space or in different other bases of non-commuting observables. And this will give you information not only about the amplitudes, but also about the phase, right? So the idea is that you then minimize some distance between your model with function and your measurements that come out of your experiment in all the bases you have access to experimentally. So the distance that we use is this Kullback-Leibel divergence, which is written here. So it's essentially a cross entropy. And you can show that this is 0 exactly when the distribution from your network is the same as the one that you get from your data. Again, I'm not entering into the details, but if you want, I can tell you more later. With this, you can reconstruct wave function from just simple measurements. For example, you can reconstruct the wave function of two-dimensional spin systems. But also, I mean, I think the thing that is interesting is that you can measure quantities that are typically hard to measure experimentally. So, for example, a typical case is the case of the Reni-2 entanglement entropy, a quantity that is very hard to measure experimentally, even with cold atoms or similar platforms. But here, by using simpler measurements or just local spins, for example, we can reconstruct the wave function on a classical computer in the form of a neural network, and then perform the measurement on the computer. So in this sense, once we have the wave function amplitudes, we can measure any other operator that might be hard to measure experimentally. So this is why this is maybe interesting for some applications. Okay, then I will finish here, because otherwise I will take too much time. But this was just to give you an overview of the many applications. There are some other theoretical problems that I will skip here, but I'm really excited to learn also about what you do and the kind of problems that you have, and about possible connections to what we do here in my group. Yeah, thank you.
Thanks, Giuseppe. So maybe we have time for a couple of questions before passing the microphone to Joao.
Can I ask a question?
Yeah.
So thank you for your talk. I really enjoyed it. I was going to ask you about the ground state problem.
Yeah.
So you shows us that unsad. Yeah, maybe you could show.
Yeah. Mm-hmm.
So you have here you talked about a specific problem, the spin chain.
Yeah. But this is just one example. Yeah, there are many applications. Yeah. Mm-hmm.
I was going to ask you.
Yeah.
The neural network would output an arbitrary, or what I mean, would search in the space of all the possible functions, right?
Yeah, essentially, when you minimize the energy, you are restricting the ansatz, to have this neural network form, yes. But it's general enough. I mean, it's quite general. You can.
Could I build a neural network that would only search for, example, in the space of functions that has a certain symmetry? In this case, for example, flipping all the spins.
Yes. So indeed, I didn't cover this part because it's like opening a Pandora box. But indeed, most of these applications, it's very important, as you know better than me, to enforce symmetries. So this can vary. I mean, from simple abelian symmetries, I don't know, translations or reflection, I mean, something like that, to more complicated symmetries, SU2 or similar. So this can be, in some cases, enforced directly inside the network. And if you don't do that, of course, you are immediately in trouble, because you will find the wrong ground state in terms of symmetry, right?
And is there a method to build these networks, or do you have to go problem by problem?
So there are some general prescriptions, so to speak, for discrete groups, and this would allow you to build general convolutional neural networks that are called group convolutional neural networks that satisfy. So essentially, just knowing the generator of your symmetry, again, assuming that the orbit is not infinite. I mean, you can do this efficiently for continuous symmetries, there are also some ways to do it. Typically, you would need to work with basis functions that have the correct symmetries, and then expand in that basis. Yeah.
Okay.
So, for example, I mean, we do this for fermions. I mean, and there you have to impose that your wave function is antisymmetric. And one obvious way to do that is to use determinants to represent the antisymmetric. So Fock space to represent the basis. And then we expand the coefficient in this basis as a neural network. Yeah. So in that sense, you move the symmetry in the basis functions rather than in the coefficients.
Okay, thank you.
Can I ask a question about the time evolution? So,
Yeah.
so in time evolution, you had, okay, you have to evolve, but you evolve a specific state, or you somehow optimize for generic evolution?
Okay. So far we've done it for a specific state. Yes. So you have some fixed initial state, and then you evolve that state. So in principle, you could do this. You could learn the generator directly, right? But we haven't done it. So something that we are exploring now is to do the evolution in the Heisenberg picture. So where you evolve an operator rather than a state, and this is a bit indeed it's more general because you could I mean it's not more general, but you could easily treat then different initial states if you are interested only in one observable, of course.
And have you done any examples, say, for example, of a scattering experiment? That's, in tensor networks now recently, there was some study of two particles colliding and seeing particle production, really a time evolution of a scattering experiment. Do you try something like that with this method? Or?
No. We haven't done it. We were trying something related to neutrinos, like oscillations, but okay, it's a different problem. But just in the high energy, but no, not scattering. Yeah, not directly at least. You can compute also spectral functions. So this is something that I didn't mention. But there are some works where it has been shown how to compute linear response, for example. And this, I guess, could be used also for applications in high energy.
Okay, thanks.
Some more questions, maybe. Maybe I have a question about reconstructing the phase that
Yeah.
So just to understand what's the rationality to change many bases, or it's like you get a denser information to sample, or
no, because indeed, if you are in a fixed basis, let's say you measure just the positions, so the distribution of your data X will be, I mean, so with this you can reconstruct only psi squared, right? Because the bond distribution. So if you want to reconstruct the phase, you need to measure in another basis and do a sort of interference experiment, no?
I see. Yes.
Yeah. So this is the main rationale between this, So
I see. Thanks. So maybe one more last question. So you mentioned that you have this Kolmogorov-Arnold theorem for reconstructing F, but what's the relation between the phi you had in the slide and the loss function? That I think.
No. This is just a mathematical statement independent of machine learning. So essentially, the statement is that if I have a high-dimensional function, I can always write it in this form. Again, as I was mentioning, the complexity is then in. But this, okay, so this phi, capital Phi, and small phi, they are all one-dimensional functions. So this is the non-trivial bit of Kolmogorov and Arnold. So in the sense that just by using two one-dimensional functions, in principle, you can represent any high-dimensional function just by taking a linear combination of n of these and then some composition of this capital phi. So this is highly non-trivial, as you can imagine. However, I mean, it has to be said that these functions phi, even though they are only 1D functions, can be very complicated because they essentially they contain all the complexity of your so in practice, if you approximate this 1D function with some basis fixed basis functions, then this becomes the representation theorem that is used in neural networks.
I see.
Yeah. So, and in that case, then you can quantify mathematically the fact that by increasing the number of basis functions that you use to represent this phi, you can then approximate this phi arbitrarily well.
I see. Thanks. And so F is supposed to have some properties as being smooth or
just continuous, actually. Yeah,
just
don't
continuous.
be smooth.
Can I also ask you about again this theorem? I didn't understand if for any f you have some phi, or if these phi's are universal.
Yeah, actually, so now I don't remember which one, but one of the two is universal.
Okay.
And the other one is function dependent.
I see. And also the small n that
the
depends
small n
only
is just
the number of the variables.
Yeah, it's just the dimensionality of this x.
Okay,
But
that makes sense.
yeah, now I don't remember. I think that maybe this is one, the capital phi is universal and this and the small phi is not. Now I don't remember.
see. Thanks.
And eta is also a fixed number that is universal, yes. So this is not written here.
I see. Thank you.
Can I ask a quick question? Is this transformer architecture relevant for you or not?
Yes. Yeah. So so we use transformers in for example, for spin for spin systems, I don't have slides, but we use it for spin wave functions. We use it also for other applications, but yeah, it's actually quite a natural idea because you can transform spins into other spins, and then you can input, for example, these spins into some non-interacting wave function. And with this, you can, for example, encode an interacting state by computing the non-interacting state on some modified coordinates, so to speak. So this idea is what we call backflow, neural backflow transformations. Yeah, okay. Unfortunately, I don't have slides about this, but so indeed, so the idea is that you transform your coordinates. Like, say, imagine that you have electrons. So you transform your coordinates of electrons into fictitious electrons, and then you input these fictitious coordinates into, for example, a Slater determinant of non-interacting electrons. And since you are evaluating a non-interacting wave function on modified many-body coordinates, this in principle can describe an arbitrary many-body state. And the advantage of doing this is that you can conserve the antisymmetry of the original wave function because you have a determinant. But okay, this would need some writing because it's not so trivial. Yeah.
So yeah, I didn't understand. I was talking about the transformer architecture that they're using on large language models, for instance.
Yes, for example,
This attention mechanism and so on. I thought this is just some way of cooking up your neural network. What does this have to
but
do with
you can see it
interacting?
in different. You can use it in different ways. So either you will use it to generate a scalar. So and then in that sense, we use it as any other application, as any other wave function, as any other CNN if you want. And okay, in that case, there is no So it's not more advantageous than using a CNN typically. At least we haven't seen a boost in performance. Or you can use it without, if you want, summing the outputs, just as a way to transform literally the spin into other spins. So that's the idea. But yeah, these are the two main, yes, but in any case, we haven't found situations where this is drastically better than using CNNs, at least for models that we will study. Yeah.